Hello everyone and welcome to this week's Simulation Moldflow Hangout. I am Kate Chappett, a support specialist for Moldflow. For those of you who have joined, typically we launch the poll questions at the very beginning and run through them. So today what I'm going to do is a little bit different. I am going to, as usual, launch poll questions. However, I'm just going to kind of walk each of you through the percentage of votes and whatnot. So I am going to go ahead and launch the first question, which is, do you typically run a cooling or thermal analysis on your mold flow designs? Yes or no? So it looks like we have about 81% of the people who have voted so far, and about 77% of you do. So that's good. So I'm going to launch the next poll question, which is, have you run a cool FEM analysis before? So this one's pretty interesting. About 50% of you have said yes and 50% have not. So at about 90% of the people who have voted so far, about 63 have run a cool FEM analysis. So I'm going to close this one and proceed to the next question, which is, what percentage of the cycle time is cooling? Is it 70, 80, 90? Does it depend on your geometry or the industry that you're in? So it looks like most of it is dependent. So 90% of the votes, it looks like it is dependent, and then 80% with 24% of the votes voted for 80%. Sorry about that. So next we'll go to this question. Are you responsible for reviewing your mold designs for your position? So it looks like about 89% of everybody is in fact responsible for doing so. Have you had a poor cooling design that has caused bad quality or price issues? So it looks like most people at one time or another have definitely run into this type of issue with cooling. And then our last question is actually, have you ever used any type of CFD software? This question is useful as we get going through the presentation today. We'll touch on CFD and Moldflow being incorporated together. Okay, so it looks about 67% of the people actually have not used CFD. So with that, I'm going to go ahead and start the presentation. So today, like I said earlier, we will be talking about shortening your cycle time with thermal analysis in Moldflow. Today on the call, we have two technical specialists, Brian Pelly, who will be talking on the side of Moldflow, and then Ryan Abel, who will be discussing CFD. For those of you who have not joined the Moldflow Support Hangout series, this is actually our third Hangout, and with the previous two being performing DOEs and simulating actual results to simulation. We commonly post these to YouTube, and we announce them through the forums, through Twitter. If you have a Twitter account, on Facebook you can find us. We announce on LinkedIn, and then we also send direct emails. And the next Hangout that we will be having will be around injection compression. So I just wanted to touch base a little bit on what's new with Moldflow. For those of you who don't know, we have the project labs, or the lab projects, which we are now offering Project Scandium for 2015. If you aren't aware, this is a free technology preview, but it does require the 2015 product keys, serial numbers, and licenses to install and run the product. Project Scandium's a pretty cool feature that we offer. It allows you to kind of preview what development has in store, perhaps for future releases of Moldflow. Some common features that we are currently running are the retractable core pins and for core shift analysis. Velocity control valve gating is one. Recently, I've had questions regarding tiger striping. I know that there's a new result for that called fill time speed that helps to predict where tiger striping could occur. But again, these are all in the developmental stages, so they're not yet released to the commercial releases. And then, as always, we also have SimHub, which is fairly new, where you can find information regarding tutorials, updates to your simulation products, not just Moldflow, but also SimMech and SimCFD. So with that, I am going to go ahead and hand over the presentation to Brian Pelly, who will discuss further what today's agenda and so forth. So Brian, it's all yours.
Great, thanks. Thanks, Kate. Can you hear me okay?
You sound good.
I'm going to assume yes. All right, thank you very much. Welcome, everybody. Today, our subject is about cooling, and it was kind of interesting listening to some of the polls as they came in. Really, I'm going to be about at 36,000 feet here, and hopefully we can drill down into more detail with future Hangouts. So, cooling is important to us because it does consume, 70 to 90% of the cycle, and it depends on industry, more importantly, your aspects or your criteria that you're focusing on as far as the product requirements. It does affect quality, like surface finish, residual stress, crystallinity, and it affects our bottom line, right? Production costs, how soon does that part reach temperature for ejection, cycle time. Not going to talk about heaters today or rapid heating and cooling or any other type of alternatives like induction. Today we're just going to do a pretty broad overview of all these different methods that we have, options that we have, and talk a little bit about how confusing that is and some optimization methods. So let me back up again. There we go. So as far as the agenda, construction techniques, I want to touch on that a little bit. That drives a lot of what type of analysis techniques we're going to use, but criteria for the analysis and types, right? Mesh types as well as analysis methods, and then a little demonstration within Moldflow and their interoperability with CFD and CFD standalone. That's where Ryan will step in. Then a quick summary. Great. So I kind of got ahead of myself there. And Kate, let me know as I talk if the slides are updating. Sync with my talk. Thanks. So construction methods. It varies. In the old days, we pretty much use a 2D drilling approach, just crisscross applesauce with plugs and ins and outs, series, parallel. We got more complex with our tooling construction methods. We started looking at basically making our tools into jigsaw puzzles and placing O-rings to get cooling in really tight places. So kind of a transition to drive-in cooling lines, water, to where we need it, where our heat loads are. And then finally, a newer trend is an additive approach, like this split approach, where we're actually creating the core through an additive process or sintering, and have a lot more options as far as what the shape, where it's located. One limitation I would say as far as scale types, there is a limited amount of scale types that are available, but it's a trend that probably isn't going away. And so we're going to kind of focus on a 3D approach for today, and that's one thing that's driving it. So as far as cooling analysis criteria, it's kind of mind-boggling when I started putting this together. So I haven't done a lot of cooling analysis in the past personally, and the variables are staggering. But there are some key things here to keep in mind. So it really starts with the part design, right? There's variables there that we can look at to try to optimize the efficiency of heat extraction, geometry, that window that we provide, say interior, right, for the heat to pass. Is it a sharp corner? Is it a generous radius at the corners? Heat flow through those corners, corner effects will be different based on the geometry. So it's something that, a term that I used with simulating investment casting is thermal modulus too, right? So surface area to volume ratios also can be looked at in this part-only mode, as well as thermal properties. So thermal diffusivity is an interesting property because it kind of combines a lot of the key thermal properties, right? It's thermal conductivity, it's calculated thermal conductivity over density and specific heat. So we kind of have a rate, thermal conductivity or speed rate of how fast we're flowing, and then this density and resistance to heat transfer, right? How much energy, specific heat, how much energy do I need to put into this material to raise it or lower it in temperature? So the bottom part of that equation is really the thermal bulk, right? And so we've got this equation that we can look at with materials in our database, whether it be polymers or core inserts. And this thermal diffusivity can be thought of almost as like thermal inertia. So pretty good thing to look at in this part design. And then we have the mold design variables that just go on, right? Temperatures, shape, location, flow rate, the types of materials that we have out there, whether they be highly conductive or moderately conductive, right? And then the construction methods and how much do they cost, right? So really, that's what it gets down to for a lot of folks is cycle time or economics, and mold cost is right up there. And we do focus on criteria as far as bottom line. So that's one of the first things that come up, highlighted in red here, is cycle time. But depending on the material, right, we could get different levels of crystallinity, residual stress, is warpage or dimension important. Some folks will use their mold as a shrink fixture, right? We could have 3, 4, 5-minute cycles. Water consumption and energy. So we're starting to change our perception or shift in how we perceive resources, energy consumption, and so that's becoming a criteria as well for a lot of folks. So there's a lot of different methods that we have as far as analysis methods that we have, and really if you think about all the different approaches in the history, it's really got to be tailored to your goals. But we have this historical boundary element method, and we have a new 3D method, FEM. BEM is really what we have in Advisor, and historically what we've used in Insight. It's steady state or average, and now we have this new finite element method where we can go kind of a combination of 3D. And so what I mean by that is there's different mesh types to the part, there's different mesh types for the cooling channel, but more importantly, we can start to look at the difference between the results. And here we've got a good snapshot of that as far as the dynamic nature of a transient or of our process, right? It is very dynamic. There is a heat flux, and we can follow these curves at surface temperature here on the core in blue, and then that flat line is an average, right? So it's a little bit different when you start looking at this in a transient, and a little bit more realistic, and this can be done again in a single cycle or a multi-cycle. So that's another important aspect to methods and whether it's important to you. So for the medical industry, or if you're running a capability study in your process, you certainly don't want to be collecting data or sending parts during a warm-up trend. And there are other factors why you may look at this as far as efficiency, scrap, and whatnot. Okay, so traditional methods is something else to look at here. So with our straight drilling approach, the way we have in the past and still do is approach it through steel materials, conductive materials such as copper alloys, beryllium copper, wear-resistant alloys, and different types of baffles, bubblers, can be produced by conventional manufacturing methods, but it's not always optimal for every part design. So again, sometimes we have to get a little creative as far as our construction methods, splitting steel or the additive approach that we saw earlier. So conformal cooling is again a trend, and the concept we see in results and studies on data that it makes sense. We're bringing cooling channels to where the highest heat loads are, and we're conforming to the part shape, and so we get more uniform temperatures, steel temperatures, and we can extract the heat more efficiently. So we get better quality, reduction in deflection or warpage, better surface quality, faster cooling, reduction in cycle time, and some energy savings. So the workflow, this is kind of tongue-in-cheek. I'll try to step through it. Again, we don't have a lot of time today to go into a great amount of detail, but the really quick pass-through is we need to import CAD, data, and that includes a channel body. So, opposed to how we've approached a beam element, we can create that in Moldflow or leverage some mold designs, 3D mold designs in CAD and lay out IGES lines, IGES center lines, right? Well, now it's a little bit different. We've got to bring in a CAD body to represent this shape. And that's what we're kind of seeing down here highlighted in the blue through this core. So we need to define the properties, and we want to do this at the CAD body level. We need to call it a 3D channel. And boundary conditions are actually set on the CAD body, and that's a little bit different than what we're used to doing. It's a CFD thing, so we'll see that. We need to assign an inlet, which we're familiar with, but we also have to tell it where the outlet is. So that's a little different for most of us. We haven't run CoolFEM with CFD. So the next step is meshing, and there's a little bit of differences there that I'll touch on, and then define the process settings and run the analysis. So we're all familiar with that. I guess to me, one of the first things that grabbed my attention is just how powerful the visualization is of 3D channels, and that is even within conventional systems. So whether that be how water flows around a baffle or through a bubbler, it's not necessarily something that is necessary to do, but from an engineering perspective, it is pretty cool to look at. I guess from a more technical perspective, you quickly, in visual perspective, you quickly see where you have dead spots, right? The blue highlights dead spots, and there's not very efficient heat transfer going on when we don't have high velocity. That, to me, is one of the biggest things as far as the types of results that you're going to see with a 3D approach. So some of the things like I mentioned, velocity, temperature, and pressure. Heat flux isn't on here, but I'll show that. And that's a kind of a different result for us as well. All right, so I'm going to jump into a quick little demo here.
And while Brian's setting up his software here, just want to remind everybody that there's a questions panel on the right-hand side. If you have any questions or for some reason your audio is not working or anything else, just let us know. And there's Kristen and Kate and myself, Royce Abel, available to try to help you out.
Thanks, Royce. Okay, so a little bit different approach here. I'm going to bring in the actual components and a total 3D approach. This is part of why I think there's going to be multiple Hangouts on this subject, because even this 3D approach can have variance. Maybe I don't want to model that as a 3D channel and use beam a combination, right? Or maybe my part design is not 3D, dual domain, right? With mid-plane, we're kind of forced to bound. So there's a lot of different things, and I'm just going to stick with a 3D approach for now. So again, first thing we want to do is tag the property. So as far as letting it know that it's a 3D channel. And then, again, this is different than what we're used to, assigning a boundary condition before we mesh. And we need to tag it with an inlet and an outlet. So it's a surface boundary condition. If you play with CFD, this would be the equivalent of setting up a flow rate, mass flow rate, and then a zero gauge or some kind of exit boundary condition. And then the properties. And this is a little different again. So there's no, our default boundary conditions with the beam approach is Reynolds number. And we don't have that here. And there's a few reasons why. This is a little bit more dynamic, and there's a little more detail, and so we don't need to lean on Reynolds number. We can look at things like heat flux and other things within CFD that are going to tell us, are we achieving an efficient heat transfer. So with that said, you know, velocity, flow rate, pressure, mass flow rate, a very awkward term for us. We're not used to mass flow rate. Maybe Ryan can touch on that when he's presenting. So you start with a part import, right? We need to assign it a mesh, whether that be 3D or dual domain. 2, and then we attack these cooling channels with the mesh, right? And the setup for the cooling channels is, there's a couple terms here that we're not familiar with. So I guess I'll leave these two alone and just kind of focus on what might be a little bit different in terms of a CFD terms. So fluid gap, a good example of that is, say, baffle blade not making connection with the tool, and you've got some flow going through a very fine gap, and what's the minimum amount of elements you want to represent that. So that's kind of an odd example, but the best one I can come up with, not being a CFD guy. Maybe Ryan can help us with that too. So enhancement layers. So for CFD folks, this is just like fundamentals, but they will do something like what we would call biasing mesh. So put a small row of elements at the interface, at the surface, again, to help calculate those film coefficients and dynamics going on at that interface. So a little bit different terms for us, but nothing too complex either. So yes, if you've done FEM, you can literally not bring in mold blocks, right? Tag the mold blocks, tag the inserts, which I'll show in a second. You can just take an envelope approach, mesh that internal and external, and then convert it to a 3D block. So one piece of steel. That's a very quick setup. So maybe we don't have all the details of inserts, components that are in the mold. And I've seen this taken to a whole different level as far as amount of detail. But again, if we look at a true 3D approach, we're bringing in more detail of the mold. So we have to tell it, what these things are, whether it be a mold block, or in this case, I think I use mold block again, but we can change it to an actual mold insert, so we get specific results to that. So, a couple of things there to keep in mind as far as how you tag it. And again, it's generally a good idea to tag this in the CAD body before you start meshing, just as far as organizing things and cleaning up your layers, which, I'm saying one thing, but I don't always practice what I preach as far as layer cleanup. So the sequence is pretty straightforward as far as setup. There are some similarities and there are some differences with CoolFEM specifically. So we do have the same approach of specifying or running an automatic cycle time. So, optimizing versus, figuring out where this cycle wants to be. With CoolFEM specifically, the finite element approach, unlike BEM, we can do transient or transient from production, or multi-cycle is another way of putting that. So there's also rather the opportunity to run a steady state. And, the differences are, again, you're going to get an average, but it's going to run a little quicker, right? With the transient within the cycle, it's going to take a little longer, but you're going to see the dynamics, as well as some solver options here. So do I want to assume a uniform temperature at start, or do I want to run a flow analysis at every iteration? So this isn't new to us. This is what we've done with the BEM approach, right? And as far as analysis sequence, the standard or the default is typically you run a cool fill pack warp, right? But we can also run a cool, rather a fill pack to, kick off that cool with a more dynamic temperature start, right? Variation in temperature. All right, so let's look at some of these results. Again, as far as what drew me to this, what kind of got me pumped about this is just quickly being able to see, especially with more complicated systems, where my dead spots were. The other takeaway for me is the crisscross plug approach does create dead spots. It's not necessarily, the end of the world or something that's important. It depends on where those dead spots are, right? And are you efficiently extracting heat? And again, that's a little different to us. And just note, we don't have Reynolds number, but we have something even better. So we can look at, basically cooling efficiency like we would with the BEM approach, or heat flux on that circuit, right? And we also have other aspects that we want to look at, temperature through, the circuit, as well as pressure through the channel. So this was a steady state average approach. And so we can see what that looks like. And then we have a transient. And I'll animate this. So looking at mold insert temp with an average or steady state, very static. Looking at the transient mold temperature or insert temperatures, definitely a lot more dynamic. I'll just animate that. I hope this update refreshes on your end. Okay, so some of the same types of optimization schemes are similar regardless of your approach. I guess one thing, we had a Hangout previously that we talked about, and it was on design of experiments, or DOEs. And so that's another thing we could tie here and to think about as far as setting up a design of experiments with the variables of melt temperature, coolant temperature, the flow rate, right? And then quality within the cooling could be, so maybe I just want to optimize my cooling design and not bring in the part design criteria yet. Run a quick DOE and just the cooling system. So take a look at average temperature, circuit pressure, a familiar Reynolds number, coolant temperature, again, mold surface temperature. So a more statistical method or approach to optimization opposed to our conventional four corners or 1-2 comparisons and done. Okay, so as a comparison between conformal cooling and conventional is consistently better with the conformal approach, and it just makes sense where if you get creative with where you're putting water, it's going to cost more as far as construction methods, but you're going to achieve a more uniform temperature in a faster cycle. So this is just one comparison between conventional and conformal on the top, and we see similar things right when we start applying conductive mold materials, copper alloys, right? We see this impact. Conformal cooling is just icing on the cake, if you will, or another approach, and sometimes we've got to be careful with the conductivity with this approach, right? It's easier to create cold spots as you move closer to the part surface with conductive materials such as copper alloys and aluminums. So bottom line, you know, max temperature on the mold, you know, difference is 35 degrees, cycle time, a split of 4 seconds, and I guess what most people are concerned with economically is how many parts can I put out the door at the end of the day. Great. So with that said, I am going to turn it over to Ryan. And Ryan, let me know if you can make yourself presenter or if you need a little help.
All right. Can you hear me okay?
Yes.
Perfect. And then how do I make myself presenter?
I will try to do that right now. There you go.
Awesome. All right. Very good. So what I want to do is show you the same model, the exact same model, run the exact same way, but really just introducing the CFD interface and the CFD workflow. And you might be asking yourself why. And what Brian just went over is really leveraging some of the CFD technology to give you the best of both worlds in Moldflow. So you're running the cooling flow channel with the CFD solver, and then you're doing everything else with with the Moldflow technology. So it's a great hybrid, and that's where some of that strange language and meshing and that's a direct cut over from our interface. So what's interesting to understand is that before the two products were combined to provide the Cool FEM solution, there were some pretty proactive molders out there using Moldflow and CFD separately. And there's different reasons for doing that. One of them is that a lot of people didn't know how to use Moldflow, but they were tool designers. So they've done a lot of tool design, they've done a lot of tool parameter tweaking, have worked with Moldflow users. But when they start looking at going from simple straight ladder channel systems to more conformal cooling channels, or really trying to dial in their tool set for high cycle performance, you can look at it strictly as a thermal problem. You can take all the plastic side of the equation out of it and just try to figure out ways to remove the heat as quickly as possible and uniformly as possible from that cavity. So that's the approach that we take in CFD. And it makes sense to use CFD if you're not familiar with Moldflow. It's easier tool to pick up and learn how to do thermal analysis for. And we've done a lot of, CFD is used in a lot of flow and thermal studies. And conformal cooling is a very challenging thermal study. So you don't get it right the first time, the second time. In fact, the people I've worked with in the past would run 30, 40, 50 variations, changing all kinds of parameters. So when you're that early in a design stage, leveraging the CFD code is going to get you to an optimal solution faster. So then you can bring that back into Moldflow with your optimized design and do some further DOE optimization, or more importantly, run the full thermal performance of the tool on top of the injection molding cycle, so we can now look at what the as molded part characteristics are. All right, so that's the general overview. I just want to give you a quick introduction to the software. We do have this feature tree workflow on the left. Material-wise, we're doing the same sort of thing. So we're going to use the same material properties, conductivities, density, specific heat. The way we assign things is a little bit different, and this is why it can be a little bit easier to use. We've always worked with 3D CAD model, so we know no other way. And when you look at designing properties, it's just CAD-centric. You pick out a part, you edit it, and then you pick what type of solid material or fluid material you want to apply to it. It becomes very color-coded as you go along. This model has been set up already. So you see in the lower left, there's a color coding. I have plastic, steel, and water. So it becomes very straightforward. And navigating through the 3D model is much more similar to navigating in a CAD system. So a lot of times people that are building steel will be using a CAD tool. So transitioning to this becomes very easy. For boundary conditions, Brian touched on this a little bit, especially the flow boundary conditions. It is a little bit different. We do put temperature and pressure at the inlet, or temperature and volumetric flow rate at the inlet. So we're specifying how fast is the flow going to move in here. It will solve for the Reynolds number, but more importantly, you're going to get all the local internal flow characteristics through the pipe, understand the interaction of the fluid at the wall, and that's where all that heat's being extracted. So then for the thermal side of the equation, we're going to do the same thing as you would inside Moldflow, which is allow heat to leave through the steel to the ambient shop environment. But now this is the assumption that we now make is a little bit different, is if we get down to the plastic, you'll see that we'll assign a plastic temperature to the surface of the molded part. This is when we start to initialize our temperature work, where we're going to start doing the thermal study after the injection process is completed, and really setting up a design of experiments saying that if the channel is if the molded part is at 419 degrees, and we know what the coolant is, and we know what the steel properties are, we can now then use CFD to look at how uniformly and how quickly the heat is being extracted based upon that cooling design. Another thing that we're able to do with CFD is we can solve for the flow properties first, and then once we know how the flow moves through all our flow channels, just clone these runs and then solve for the thermal properties by themselves in a transient manner. So we're able to decouple the flow and thermal solver, and that's really important because here the flow solution takes about an hour to solve, but the thermal solution over a 30-second cycle takes like 20 minutes. So we can look at doing a thermal cycle with copper, doing a second cycle. We can start to layer these cycles on top of each other to create those transient plots. just looking at 20 seconds per cycle. And it really just speeds it up and allows you to make thermal changes and just do thermal runs on top of that already solved-for flow solution. So we're going to look a little bit deeper now at this 30-second cycle. We're saving out all these different time steps now. You can be very selective on how quickly we start and how quickly we save. So we initialized everything to a hot temperature, and then very quickly things start to cool off. So let's go into about, let's see here, 10.5 seconds. We can set the legend here to the range, and we noticed right away that this, where we have those channels coming in on the left-hand side, this is where our inlet to that conformal cooling loop is. This wall is cooling off the quickest. It's being cooled by the inlet to the channel. It's being cooled by this horizontal run. So we can see the temperature variation across here is cooling off in this corner first. That could be a problem. It may not be. But if you're looking to come up with a shorter cycle, uniformity is everything. So trying to limit those variations is very key. So when we look at the results, we can just modify the legend a little bit to try to get more of a range. So now we're looking at about 9 degrees variation. This is 10 seconds into the cooling cycle, and the top is 9 degrees hotter than this left side, and then the right side somewhere in the middle. So we're starting to really visualize not only what the tool temperature is, but what the part temperature variation or rate of cooling that part is going to be. So the last thing I want to get into is another reason why using CFD for early optimization is so enticing is our brute force type of way of comparing results. So any type of runs you have up here, and I just did 2 cycles and then changed the insert to copper, you can go through and create an image and have the software pull those same images out for you into a row of thumbnails. So without even opening up these results, we can create a side-by-side image and say, well, what does the inside steel look like on the first cycle between steel insert and copper? So we can see how much cooler it is, but the gradients, tend to be relatively similar. Looks like maybe there's a slightly less range from min to max. So let's take a look at the second cycle. We just drag and drop these thumbnails right into the screen to see what the second cycle looks like. And this is a fully dynamic comparison environment where you can just modify the legend to tighten up your range, and then the other design you're looking at in the right-hand screen is going to modify real-time as well. So we are comparing a lot of different alternatives, whether they be flow rate, materials, or geometry. This type of real-time comparison just makes it a lot easier to get through a lot of data very quickly and identify trends. So another way to extract data is to draw lines in here in the results. And one type of, so I put a line right inside the center where all those cooling loops were. I think my screen just locked up here. Brian, if you're still there, can you pull back sharing and give it to me again? Oh wait, whatever you just did, I got it.
Oop, yeah. Magic.
Yeah. So skipping how to show the plots, basically we're just creating a point plot right through all the tips. So we have all these loops in here that are designed to pull heat out of the plastic. So this is showing you the rate of how much heat is being pulled out. This is the energy, the watts they're pulling out per area. So we can see that the designs have drastically different performances, one being metal and one being steel, one being copper. The copper designs are pulling less heat out through the through the cooling channel. You're putting less strain on the channel because the heat is just conducting towards the ambient better. And you see the variations between the different loops. We have the first 4 loops, and then this is the middle one where you have the streams crossing back on top of each other. This one actually cools the worst. Seeing something like this, you can probably loosen up the cooling on this side, maybe bring in some cooling in the middle, and try to cool it from the middle outward. So the rate where the cooling starts and where it ends, you start building in residual stresses. And these are the type of things that we're trying to design out of the part, but at the same time, we're also allowing you to take those residual stresses into a structural tool to find out what the strength is. So on these comparison lines, we can then look at anything, any parameter that we're solving for in CFD. Let's just go back to something simple like temperature. So we can see the temperature from left to right on this, this corkscrew double pass cooling system. Again, the range of temperature here is a lot less than it would be without this system. But these things are very costly to build. So putting a little bit of time up front to make sure that you're making it as efficient as possible just gets a little bit more cycle time out of your runs and better quality parts. So I think that's all the time I had to show in the result in CFD today. Brian, do you want to take this back and show that the last slide for us?
Yes, sure will. Thanks. Yeah, the thing for me was with CFD, there's a couple of questions coming in, and yeah, if you're going to run a 3D channel, in Moldflow, you do need to use the CFD solver, so it's coupled or interoperable. But as a customer, having that product, what I found myself doing quite easily, like Ryan pointed out, it's very CAD-like. We're picking on surfaces for boundary conditions. The meshing is somewhat automatic, but the time to just creatively go through some shape factors on cooling and see the flow, actually see the flow is some of the things that impacted me as far as the visual aspect of it, how fast it ran, simple things. For statistics, that's another issue in itself. And let me see, am I sharing my screen? Anyone? Ryan, Kate?
Yeah, I can see your screen.
Yeah, we're on the what?
Yeah, we can see your screen.
Awesome. Great. So yeah, and that really gets to my next slide. Thanks, guys. So which method to use? It's sometimes it depends on what tools you have, but conventional versus conformal, and really it depends on your criteria really, as far as you got to factor in your mold cost and is cycle time, what the material is as far as residual stress or crystallinity, right? These are all factors that are gonna help you decide which is the right approach there. And if you're going conformal versus conventional, there's a high likelihood you're going to need 3D, and that's really the separation between, do I use beams or 3D? What's the shape of your channel? Is it well represented with beams? It's a very efficient approach. You can use a combination, but really it's criteria versus computational time is the decision there. With 3D though, some of the advantages are definitely visualization. It's popping. It really is much easier to look at, and takeaways happen quite fast. And again, geometry, it drives that. So BEM versus cooling, there's a lot of times, where whether it be mid-plane or fusion or 3D, where the geometry tends to overlap itself, and really the BEM approach is finite different. It's solving globally. It has convergence issues with those types of geometries or mesh that will overlap, and those convergence issues just turn into really long run times or fails, right? The analysis fails. And so within them, we'll kind of go from mesh type to mesh type. Well, maybe mid-plane doesn't work, but dual domain might versus 3D. And sometimes you're more likely to get a BEM to converge with a 3D. There's less, assumptions going on with the 3D part mesh. But really, it ties to the quality, whether you have overlapping elements that confuses that finite difference approach. And steady state versus transient, again, it's really how much you need to see the dynamics. Transient is going to take a little longer as far as computational time, but it's going to give you a lot more information as far as true dynamic thermal footprint, as well as warm-up trends. Criteria versus computational time, and that really is, it depends on your criteria, and obviously that'll drive the approach you take. CFD, Moldflow versus CFD, I think there's some synergy there. Certainly there's approaches where you're going to be just using Moldflow independently, but if you have CFD as a tool, there's a lot of approaches there that are going to help create a more efficient optimization scheme. And speaking of which, there's plenty of others, right? There's other FEA packages out there. There's also people using like metadata collection systems where they're pulling from different products like Moldflow, CFD, whatever the product is, and then collecting that and harnessing that statistically to drive optimizations. That's a little bit more complex than our garden variety company, but people are looking at that. The split there is, okay, am I optimizing in the Moldflow product or Moldflow CFD in conjunction, or am I doing that outside, and that's just one of the tools, right? So within the software, this is our classic flow for optimization cooling. And it really, again, it depends on your objectives or criteria and what can be changed. And sometimes that boils down to economics or tool life, right? So there are some limitations with the additive approach in those steel types. Selection of types are limited, and some of the bigger complaints is tool life. So this is just kind of a quick slide on how complex things are, right? What is the right approach or right problem at the right time? Some people are doing this at the part design level and may not add the mold design detail, and that's kind of the path as you move forward. There's plenty of options as far as how we optimize. Do we use 1D beam, beam elements, 3D channels? And when we get into the tool design, we can start taking a more 3D approach, right? Apply 3D channels. We have the option then for steady state versus transient. Again, if you follow the arrow on the bottom here, we're optimizing, but it depends on the criteria, right? And what that is. At the end of it, I think me as a Moldflow user, I'm always going to come back and validate it, within Moldflow. And again, maybe I don't go outside Moldflow, and there are some statistical methods that are growing, as far as usage and as far as capabilities, or DOE approach. But no doubt when you get to this point, you've added all your detail, and it's going to be longer runs, and it may be multiple runs. It will be if you're optimizing, right? Whether you apply DOE or you're just doing a corner approach or a two-variant approach. So in summary, I guess understand your decision criteria. That's where we want to start with any type of simulation or analysis. Balance criteria versus time, right? And that means modeling time. And that is one of the advantages I've seen with a 3D approach. I find less modeling time. sometimes the analysis time in the FEM approach is actually, due to mesh quality driven by geometry, is faster. You don't perceive that at first. You see this finite element method that is, oh my gosh, millions and millions of elements, but that convergence issue that you have sometimes with BEM causes a failure or a really long runtime. Results in interpretation, right? Sometimes you can visualize things quicker than numbers, so it's a little bit more visualization with a 3D approach as far as balance, in my opinion. But you got to use the right tool, you know, for your job, for your company, for your requirements, and you have to look at optimization as an approach and map that out, and that only makes sense for the product that you're developing or the company goals that you're developing it for. So with that said, I'll turn it back over to Kate.
Thanks, Brian. That's about the end of this week's Hangout. I want to thank everybody for joining us today, and I especially want to thank Brian and Ryan for presenting in this week's Hangout. The next Hangout will be in about 4 weeks. At the end, when this Hangout ends, you'll be prompted with a survey, so if you could fill that out, we would greatly appreciate it, as we do look into those and take into everyone's into consideration. If you end up having additional questions, you can always post them to the forum. And lastly, we do upload the Hangouts to the YouTube channel, so you can always reference that later. So with that, thanks for coming, and see you all in 4 weeks.